And the last topic for tonight is the autoionization of water. So if you look really, really closely at a glass of water, you will never see this going on, but it is happening, trust me. So what goes down in a glass of water is H2O, which is a liquid, is dissolved or mixed with H2O, also a liquid. So we've got water molecules surrounding water molecules. And what happens by default, you're not going to believe this, but trust me, it occurs. Water will actually donate protons to itself. So that makes this an acid and this a base. So water can ionize itself. That's why it's called autoionization, just like an autobiography is when you write your own book. Autoionization is when you ionize yourself. And so what you end up with is H3O plus and OH minus. And of course, this little system right here, H3O plus is going to donate a proton back over to OH minus. And so we would end up with equilibrium being set up here. And this would be the conjugate acid and the conjugate base of its own system. So this is going back and forth, and you would end up having this occurring very, very often. Another way that we can write this, and another way you will see this written, is H2O autoionizing itself in this form where it just breaks apart into H plus and OH minus. The difference between these two forms, they're saying the exact same thing, literally. The H plus, that's what we normally consider when we're talking about acids, but H pluses don't usually float around by themselves. They're going to attach themselves to, remember, water structure as a dipole. We've got that dipole negative right there. So those H pluses are actually going to be attracted to that guy, and they're going to bond themselves that way. And so what we wind up with is H3O plus molecule. So really there's no such thing as H plus. All H pluses are really H3O pluses, but who wants to write that many letters? So we just call it H plus a lot of times. Okay, this is all going somewhere, I promise. So what we can see from this then is since we're set up at equilibrium, that means equilibrium is established. So what do you know? There's an equilibrium constant for this, and we call it Kw because it's the equilibrium constant for water. So the equilibrium constant for water is a constant. So the Kw for water then, since all of these are liquids, they don't really get counted into the equation. So the Kw is just going to be the product of the products. And so if we look at that top equation, it would be H3O plus times the concentration of OH minus, and it's a 1-to-1 ratio. Now, a cleaner way of drawing that, and the way you're going to see it most often, that's going to make the most sense, is actually with that second equation. So let me get rid of this stuff real quick. And so that's going to be the concentration of H plus times the concentration of OH minus. Because these two equations are really showing the same thing, this is just a simpler way of writing this up here. So the Kw would be the concentration of H plus times the concentration of OH minus. And that, luckily, is a constant number. So Kw, which is H plus times OH minus at 25 degrees Celsius is always equal to 1.0 times 10 to the negative, blast. I'm going to have to write that down here, 1.0 times 10 to the negative 14th. Okay. So at 25 degrees Celsius, you can calculate the concentration of H plus or OH minus based on this little idea right here. All right, an example of where we can use that would be in this question right here. So the concentration of OH minus in a solution is found to be 1.4 times 10 to the negative 11th molar at 25 degrees Celsius. Find the concentration of H3O plus. So the trick is with this autoionization, so let's write it real quick. H2O autoionizes into H plus OH minus. With pure water, all of the H pluses that form are going to have an OH minus partner to balance them out. So really water is never going to be anything but neutral because every H plus that's created is going to be OH minus. If you introduce something into the system, though, that throws off that balance, so messes up the equalness of those two, you're going to wind up with something that's either acidic or basic, depending on what's added. So in this particular thing right here, our concentration of OH minus is 1.4 times 10 to the negative 11th. And since we know that the Kw is equal to the concentration of H plus or H3O plus times the concentration of OH minus, we know the Kw, we know the concentration of OH minus, we just need to find the H plus. So it would be 1.0 times 10 to the negative 14th equals concentration of H plus times 1.4 times 10 to the negative 11th. If we go ahead and solve that out, then the concentration of H plus winds up being 7.1 times 10 to the negative 4th molar. Now, something interesting to note about this, if I get rid of those numbers real quick, we compare the concentration of OH minus, which is 1.4 times 10 to the negative 11th. We get that right there. And the concentration of the H plus, which found out to be 7.1 times 10 to the negative 4th. So is this an acidic or basic solution? The answer is it is acidic because you can see that the concentration of H plus is higher than the concentration of OH minus. And since we have more of the H pluses, that means it's going to be in the acidic realm. If there's more OH minuses, more hydroxides, then it would be basic. And if those two were equal, then it would be neutral, which would be pure water.